Welcome to another GC Basic demonstration. This is part 10 for the 16F chip family legacy chips that I'm doing a set of videos for. I'm really re-baselining the legacy chips, and this applies to 16F legacy, 10F legacy, and 12F legacy. And I've explained in the previous videos what legacy means. So if you'd like to like and subscribe and let the video run all the way through, and thumbs up, etc. Be very grateful. So EEPROM, we're going to show some values of the EEPROM on a serial terminal. I'm going to give you some other insights as well with respect to constants, which is sort of quite important. So let's get started. I'm assuming that you've got all the prerequisites. You've installed the software, GC Basic, the GCStudio IDE, programmer works, you've got your PIC working, LEDs working, a pot, switches, serial USB TTL converter is operational, and you got the LCD. And this is another case of where you can do some of this stuff on an LCD, but putting in that $2 USB TTL, it just revolutionizes debugging and showing information. So I'm using this board. It's a PIC10 plus demonstration board. Cost about 15 British pounds, sorry, and it looks like this. It's got on it, I'm using a 40 pin. I could have used a 28 or a smaller. I guess that's a 20. I'm guessing that's a 20. Use a 20. LCD, LEDs, potentiometer, clocks not installed, EEPROMs, external EEPROM, external sound, serial. It's just great. This board is one of the best boards I've actually ever seen. I love it, absolutely love it. No change to the hardware layout, exactly the same as it was before, because EEPROM is internal to the microcontroller. So we're talking about memory. Let's just get a baseline on memory, which EEPROM is one of the classes. This particular chip comes with 8K of flash program memory, 512 bytes of data or SRAM memory, and 256 bytes of EEPROM. I could not find in all the microchip documentation a memory map for this chip. So we'll have to put up with this. But what you can do, you can go out to GCStudio or PICInfo, sorry, go out to PICInfo, and you can see a lot of this data up here. If you look in the chip data, it says here the program memory is 8192, 256, 512, and stacks, I guess the stacks are 32 or 28. What's stacks? We've got stacks listed. Yeah, stacks of 16. That's not many in actual fact. Let's get back to full screen. So what we've got is 256 bytes of EEPROM. So what does that mean? That's the electronically erasable programmable read-only memory, non-volatile. Okay, you can store small amounts, 256 bytes on this particular chip, but it does allow you to store them in byte values, and you can erase one byte and put another byte back. So you can replace just one byte. It's not like a big block of memory. It's a byte by byte erasure and programming capability. They're there for long term, and they're very robust. A couple of things that I was going to mention about constants. So you have a set of constants that are available. And with respect to memory, the program, the 8K, is exposed as something called chip words. The EEPROM is exposed as chip EEPROM, and the RAM is exposed as chip RAM. So in your program, if you want to know how much stuff you've got of a particular type, you can use chip EEPROM. Again, if we go out to PICInfo, and if you haven't started PICInfo, press function key F4, and then type in PICInfo, it will come up. You select your chip on the front, on the select tab. I've selected my chip here, a 16F1937, and in the chip data, it lists many of the constants that are available to you. So if you wanted to know what chip family it is, how many UARTs it's got, the number of stacks, the maximum frequency, the default frequency. What's that? Oh, that's the default frequency. It will always default to the max frequency anyway. How many pins it's got, etc. Constants are what should hold your programming environment together. So what we're going to look at is loading data into the EEPROM 3 ways. You can do it, one, programmatically. Second, you can actually store tables in there and then use the table commands, which is your all public commands. Or you can actually, with the more recent releases, just create raw tables straight into EEPROM. And you can mix and match them all together. So there's 3 ways of doing this, and later on we'll look at writing into the program memory as well. But this is specific to EEPROM. So in the sample code, we will read and write to EEPROM, and we're going to put the results on the terminal. Now I'm going to just take that out because that says set up the PPS. PPS is legacy, not legacy. So we're going to write some values to the EEPROM, read the values back from the EEPROM and see the results on the terminal. And then we're actually going to use a program that will also see the results. And then we can check out some chip constants, the chip specific constants as well. Let's get the program up. Let's get into the IDE. Here is the IDE. It's empty. Press enter the Explorer. Top left is one way of doing it. And showing EEPROM data, program 140 and 150, 160. Let's pull all of them up in one go. 140, 150, and 160, which is showing EEPROM data to serial terminal, showing table EEPROM data to serial, and ensuring the program matches the chip specified. Control B or close that. If you close that, you can close it by doing that. Great. You learn something every day. I've still got program 60 up here for some reason, don't know why. Right, let's start with 140, which is showing EEPROM data to the serial terminal. We've seen most of this before, but I'll zoom in for you. Chip selected, option explicit, etc. None of the constants here have changed. None of them. They're all set up as they were previously. And if they were, we should have two sets of serial, because I've obviously done that twice. GC Basic doesn't let you redefine a constant twice, but it doesn't really harm if it's the same value. So what we're going to do is set up some byte and word variables. Why do we need that? Well, we need the EEPROM address is a word address. It's bigger than 255. It's a word. We have to pass the function that we're going to be using. It's a function. We'll have a look at this. It's a function. And an EEPROM address as a word. We have a bit of a delay, and then we have a do loop that does it forever. And essentially, it's going to do a lot of preparation stuff on the screen, preparing the terminal for our display. More stuff about preparing the display, but then down here, eventually, it says send EPWrite. EPWrite. Write the EEPROM address with some data. And where's it going to get that from? Make sure we can see it on the screen. I might have to change the zoom level here. Yeah, I'm going to have to change the zoom level. If I could do it for us, there we go. There we go. We have a for next loop here called EEPROM address. And look, it's got EEPROM address, a for loop. We haven't seen a for loop before, I believe. From 0 to chip EEPROM. And chip EEPROM is one of our constants. So it's going to go from 0 to 255, which is 256 bytes. It takes this address here and passes it in this subroutine here. And it says, write the value of out data. and the value of out data is just calculated. Look, it could be random. I give you some options, some fixed value, or it's a calculated number. So it's going to be 255 less the address. So effectively, it's going to write 255 to byte 0, 254, 253, 252, etc. And what we're going to do is we're going to read it back with a public function called EPRead. Same address, read it back in. I do read it in, I do set it to 0 before it comes back in, just because, just make sure it's I cleared it down so you're not being kidded. And then I put it on the screen. Let's have a look at this. Got my terminal hooked up. I'll clear the terminal, make it a bit bigger, change the font in a second. Might do it twice. Oh no, beautiful. Oh no. I'm going to do it twice anyway because I'm going to turn the time off. That was left up for the last demonstration. Have I got the reset working? No. Hard reset's off. Let's just reprogram it quickly. What we got is a series of values there shown on the screen. Clear that down, and then we'll examine the results. Great. So it says here, EEPROM test and show results. That's the string. Then we sent out this header here. Then we sent out some formatting down the side. And it says here that the values that are in there are FF, FE, FD, right the way through to 0. Something has written those out. Our program. Use the public functions of EPWrite and EPRead. So if I change that to out data is 255, or sorry, 55, which is 85 hexadecimal, it will set all the EEPROM values to 85, but it will show it as hex, so it will come with 55 hex. Extremely simple, but let's pretend you don't believe me. Program it once more. Whilst it's doing that, I'm going to open up PICKitPlus, which is the user interface for the PICKit software that I sell. Whilst I did that, of course, it failed to program because I had two things accessing the PICKit at the same time. Here we go. I'm just going to zoom out for us. Great. Now, got it connected. You can see all the buttons that you need to see. I'm going to check here. I'm going to uncheck there. I'm going to read that in. It says it's powered, which it is. And it says here it found through the programming interface, not through the serial interface, FF through to 00, which is exactly the same as we have on the terminal. So the function works. So you can write data out. Extremely simple. EPWrite, EPWrite, and EPRead. Let's keep this going. Another way of doing it, same header, same error there. Look, that's a duplicate. I shouldn't have that in there because you'll get confused. I've written a function here called show EEPROM, and we'll have a look at what that does because it waits a second. It set up all the terminal, remember, show EEPROM, then does a do loop. So what's it doing? Well, you can actually load data into the EEPROM just by doing this. Look, you can say EEPROM, give it a name, where you want to locate it in the EEPROM memory. That's at 16 decimal or 10 hexadecimal. Put some numbers in there, look, 1 to 6. Look. And I want another data source at 16. I don't know what number 16 is. And it's going to be the values of 1, 2, 3, 4. And the show EEPROM routine is essentially a read. It just reads it in and puts it on the terminal. But this is very different because I can now put in different types of data. These are numbers. So if we program that, when then we'll read it, we'll look at what it says on the terminal. We'll see that we can put numbers in with some ease. It's programming it. It's done it. We'll look at the terminal, and here's the terminal. And it says in here that there are some numbers here at 10hexa16, and it goes 1 to 6. Then after that, at address 16, it says hexadecimal 11 to hexadecimal 16. But watch this. If I change this to a string, we will get a slightly different result, because in our terminal here, it will have the hexadecimal string for hello world, and we can read that back in using EPRead. Very simple. And here it is. It's this big long string here. Look. But how would you know what that is? Well, I can quickly show you in here. I can read it into memory here. I can put that as byte ASCII, and it now says in the programming software, hello world. So we can use number strings, constants. We can do all the things that we can do inside of this, what's called a table. So that's pretty cool. I'm going to put that back as it was. That's good practice so that the demos work. So that's introduced the concept of writing structured data programmatically into the EEPROM. There are other ways of doing that as well. There's tables that you can do. I won't cover tables. You can do it because these are better. You can use this a lot easier using the EEPROM and EPROM command set. It's a lot easier than using tables. But here we go. I want to show you this. Same header. What we're looking at here is a way of checking and using some of the constants that are automatically in the microcontroller to help you after you're running a project. We'll pretend your use case has got a project, and I don't remember. You've ended up with a hexadecimal file, and that hexadecimal file is suitable for one type of chips. Well, you can use constants to validate that, and so if the header is the same, all this does is print out to the serial terminal, and it could be to the LCD, remember, what the current chip name string is. It says chip name string, GC basic demo. But what you can do, you can hard code a string and test against it. Therefore, if in the future you loaded a hexadecimal file into the wrong chip, you could have an LED flash or the LCD or the serial go, hold on, the target chip doesn't match what is the current chip, and that's the current chip. Target chip is a string, that's the current chip. It will actually give it an error message. So we're using constants here, and they're in blue generally. The majority of them all in blue now. I'll just clear that one down. Microcontroller is correct. The program is intended for a 16F193. Well, let me explain what's happened. It's ended. The chip has gone to sleep before the buffer has ended. So if you put a 100 millisecond delay in that, it will resolve that. It's just the chip has literally gone to sleep before it's emptied the buffer out. It's amazingly fast, and microcontrollers are quick. I just did that wrong there. Never mind. I'll just check. Just get it up. There we go. Look. The microcontroller is correct. The program is intended for that chip. Even 100 milliseconds is too fast. If that fails, all I'm going to do is do that. Put that on 2 lines. That will just make it slow it down a little bit. There we go. 1937. Just needed a bit of help. I don't think it needs a 1 second at the end there. 10 milliseconds will be ample. So, what have we seen? We've seen how to read and write values to the EEPROM. We've seen the results on the terminal. We've seen the sample code. We've gone through and looked at chip-specific constants and seen those results on the terminal. These are what's called public functions. They're available on all microcontrollers, legacy and the newer chips. Okay, we're going to go somewhere completely different on the next video, I2C. Enjoy.